Hey y'all, welcome to just a general lesson. I'm doing some practice ice tables today. Um, I'm not there in the DP chemistry curriculum, but I thought might as well get some of these out of the way for anyone who needs to learn how to do an ice table. Now, generally when we do ice tables, we are talking about two separate situations. Either we have some known values for equilibrium and initial conditions, or we do not have known values for our equilibrium conditions, but we know our equilibrium constant. So first off, what does I stand for in an ICE table? Well, I stands for initial, C stands for change, and E stands for equilibrium. So when we're doing an ICE table, what I generally do is I'll set it up as ICE, make a little table right under my equation, and divide my equation up with every reactant and product giving its own cell. Now, a couple things. One, these are always concentration values. So it's going to be mole decimeter cube inverse. Always, always, always. So I'm just not going to write units on anything. Second is water doesn't have a concentration. It's our solvent. So we're just going to ignore the water column here. All right. With that, we're going to do a practice problem. In this problem, we're going to say we know our initial for ammonium or for ammonia, sorry, NH3 is going to be 0.350 moles per decimeter cubed, and we know our final is 0.325 moles per centimeter cubed. But the problem is we are looking for Kc. We do not know what that is. So this is one of my favorite types of ice tables. All we're doing is just solving for the equilibrium constant. This is the first type, and when you solve for the equilibrium constant, it's honestly the easiest. So we're usually starting off with zero of our others. This assumes we just took some ammonia, dropped it in some water, and we let it kind of dissociate and become sorry, not dissociate, but react with water to become ammonium and hydroxide. So what we first have to do is figure out our change column. If we went from 3.350 to 0.325, we know that we decrease by minus x. X is some amount, and we can actually calculate it here because 3.5 or sorry, 0.35 minus 0.325 is 0.025. So that just comes from basic math. If we add these two together, if we get that, assuming that's positive, or this minus this gives this. So that solves the change for ammonia. Now, how do we figure out what the changes are here? Well, it turns out 1 mole of ammonia makes 1 mole of ammonium and makes 1 mole of hydroxide. This is just balancing equations. We know it's a 1 to 1 to 1 ratio. And because of that, if we lose 0.025, we gain 0.025 for each of these. Now, we finally can get to our equilibrium values. 0 plus 0.025 is 0.025 and 0.025. So we now have our equilibrium values for each. And I know that I can find the equation for our equilibrium constant by just setting the concentration of my products raised to the power of their coefficient to 0.025, again, raised to the power of its coefficient, divided by the concentration of our reactant, 0.325, raised to the power of 1. And when I plug this into my calculator, I just get 0.001795. I'm going to round to 3 sig figs. In this case, technically, I'd be rounding to 2 because as I multiply these together, so you know what? We'll just round it to 2 sig figs, and we'll get our answer of 1.8 times 10 to the minus third. So that is my value for Kc. So that's the first type of ice table equation. We are solving for the equilibrium constant. And so we were able to do that quite well. Now we'll move to our second type of problem. This one's going to be a little bit more challenging. Let's assume that we have some acid, HA, and in water, that acid dissociates into the A minus, the conjugate base, plus H plus, its proton. This is all aqueous, of course. So how do we actually figure out what happens if we have a known Kc? And for most acids, we actually know the Kc at given standard temperatures. In this case, we know the Kc is 1.6 times 10 to the minus second. And actually, with acids, we don't actually call it Kc, we call it Ka, the equilibrium constant of acid or the acid constant. So, how do we actually find our volumes? Or, sorry, how do we find our final molarities if we are given an initial one, which we might say initially we have 0.150. So, how are we going to find out what our, if this is our initial, how do we find equilibrium value? Because we know not all of it's going to convert. So, of course, we're going to use an ice table. So to set this ice table up, we're actually going to set it up exactly as we've done the previous one, I, C, E. I'm going to separate out my values. And of course, we know our initial values are going to be 0 and 0 for the products, and we also know it's 0.150. But now we don't know the change because we're looking for these equilibrium values. So we have to do what we do in math when we don't know a value and we need a stand-in for a number we don't know. We're going to use a variable. So we're going to say we decrease by some amount x. Once again, because our coefficients are 1, if we decrease by x, we'll increase by x. And our final equilibrium values will be 0.150 minus x. And our equilibrium values for others will be x and x. So now we just have to plug it into our equation for Kc, which we do actually know this time. It's 1.6 times 10 to the minus second. And that's going to be equal to x to the power of 1 times x to the power of 1 divided by 0.150 minus x to the power of 1. So to simplify, we have x squared divided by 0.150 minus x. And that, once again, is equal to 1.6 times 10 to the minus second. What I'm going to do at this point is I'm going to, of course, just simplify this. I'm going to try and put everything on the same side. So as I simplify x squared, it's going to be then equal to 1.6 times, oops, not x, 1.6 times 10 to the minus second. That will be multiplied by 0.150 minus x. That part will simplify, of course, further to 2.4 times 10 to the minus third minus 1.6 times 10 to the minus second x. All right, we are almost there. I'm going to move all of those over to the same side to make a quadratic equation. So this is going to be x squared minus, or sorry, plus 1.6 times 10 to the minus second x minus 2.4 times 10 to the minus 3. And that's going to be equal to 0. So we're almost there. You can start seeing why this is my least favorite kind of ice box. It takes a bit of time. If we think of this as a quadratic, we have ax squared plus bx plus c equals 0. So in this case, a is 1, b is this value, c is this value. And we can also solve a quadratic by the equation x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. This equation, I believe, is in the data booklet within one of the first two tables. So you don't need to remember the quadratic formula or how to solve quadratic, but you do need to be able to plug these values into a calculator. So substituting our coefficients for x as values into the quadratic equation, I'm going to get x is equal to 1.6 times 10 to the minus second plus or minus the square root of 1.6 times 10 to the minus second squared minus 4 times a, which is 1, times c, which is negative 2.4 times 10 to the minus third. So those negatives will cancel out. And we'll divide the whole thing by 2. Because once again, a is 1. When I plug this into my calculator, because of this pesky little plus or minus that we get for a radical, remember that when you have a square root, the square root of 4 is 2 or negative 2. They're both answers, so we always have to do plus or minus, but that is beside the point. So as we plug it in, we're going to get x is equal to either 0 0.0416 or x is equal to negative 0.0576. So we have two values for x, only one of them can be right. Well, we know we can't have a negative concentration here. These cannot be negative values because we know for a fact that they are changing in the positive direction. So that means that our negative value is actually impossible. Therefore, this must be our correct value for x. So now we can just plug that in and we can find that our final concentration of HA at equilibrium is 0.150 minus 0.0416 for a final concentration of 0.108 moles per decimeter. Mole per decimeter cube inverse. So this one is a little more extensive. Usually you need to use a quadratic formula. It gets a little more difficult in that case, but it still won't overall be too bad as long as you're plugging things into your calculator and keeping your algebra straight. Anyways, I hope this helps and have a great day.